Okay. So on behalf of the Three Rivers chapter, thanks everyone for attending. This is the first of an 8-series talk on Agile MBSE and various topics in that domain. And it's going to be given by Dr. Bruce Douglas, who is esteemed, written many books. I have his book. So we've really been working a while behind the scenes to try to get Bruce to come and organize this lunch and learn. So we have a couple of introduction slides just on what INCOSE is. I'm going to talk a little bit about what the series is going to look like. We're going to send out a survey at the end of every one of these talks, ask you guys what you were interested in, if you liked it. We might pivot, at the end and bump off the last 2 talks to bring in some other talks if the interest of the quorum goes a different direction what we're proposing here. So. Thank you all for coming on behalf of the Three Rivers chapter and the other chapters in the region, which I'll talk about in a minute. And we also want to thank our sponsor for the first couple of these, which is Smith & Nephew Robotics. So this is what the series is looking like. It's sponsored by the Three Rivers chapter, the Heartland chapter, the Michigan chapter, the Wright Brothers chapter, and the Canada chapter. So we all pulled our membership dollars that comes from you together to be able to offer this. So we're going with kind of themed months. So September, October is going to be Agile modeling. October, November will be use cases and requirements. November, December is going to be ICDs and handoffs. And then January and February will be testing and MBSE patterns. So this is what we're looking like. For the series. Again, we're going to send a survey out at the end of every talk. Tell us what you thought. Tell us what you're interested in going next, and we might pivot halfway through. We do have the first talk nailed down, which is today, and we also have the next one, which will be in 2 weeks. So October 6th, we're looking at sticking to a 2-week cadence. So that'll be another thing we'll ask about in the survey is that too close? You want it spaced out a little bit more? Let us know, and we'll respond appropriately. What's INCOSE? Looking from the registrants, a lot of people aren't familiar, aren't members. INCOSE is the International Council on Systems Engineering. We're a not-for-profit organization of volunteers that are really out there to, improve the system engineering knowledge and, push out systems thinking. It's an international organization, 1,800 members, 74 chapters, 35 countries, and 55 different working groups. And I'll show an example of some of the working groups, but broad spectrum from requirements to MBSE to Agile to a lot of the fundamentals in systems engineering. So everybody here who worked to get this together, pretty much from a not-for-profit volunteers, and we're really trying to respond to what you need and what your interests are. So again, fill out the survey and let us know. We'll get in additional talks, and we're continuously lining up speakers and things. If you want to know more about INCOSE, go to INCOSE.org. Check out the chapters. This is the Great Lakes region is really the region that's putting on this event today, but there's other regions that might be in your area. And you might want to get interested. We have lots of different events going on all the time. This just shows a map. So there's three sectors of INCOSE, and we're out of the Americas region. This is the Great Lakes region, so we're made up of various chapters that shows the location. Canada chapter really has condensed into one, and with with COVID and the progression of the pandemic, one of the advantages has been actually that we can do more virtual meetings like this. So we've kind of gone to a regional model where we have combined talks, and we can get speakers that we wouldn't normally be able to bring in. This just gives you an idea of some of the corporate advisory boards that we have on here. So General Motors, Ford, Boeing, Idaho National Laboratory. So we have a lot of corporate sponsors. So this is going to be on the slides. If you download the slides, check it out, see if your organization is one of the CAB members, and you can get access to all the INCOSE content on the website for free. All you got to do is log on. This is some of the working groups that we have. So we have 55 different working groups. And there's Agile Systems Engineering, Complex Systems, Configuration Management, Human Integration, Smart Cities, social systems, training, transportation. So a broad spectrum of working groups that are generating content, practices, best practices, style guides, procedures, lots of good content here to leverage and to help you solve whatever problem you're trying to solve. So to learn more, visit INCOSE.org. As always, we're looking for people to help. Volunteer organization can never have too many volunteers. We're looking for people to help organize meetings, run down talkers for us. And we're also looking for corporate sponsorship to help, bring more talks and more content like what we have here. So without further ado, let me introduce Dr. Bruce Powell Douglas. He has deep and broad expertise from over 40 years of experience, specializing in both model-based systems engineering and model-driven development for embedded software and safety critical systems. He's developed systems in a number of subject domains, including aerospace, defense, medical, automotive, and telecommunications. He's a co-author of the UML and Sysmol standards and is the author of over 7,000 book pages from a number of technical books, including Agile Model-Based Systems Engineering Cookbook, the Agile Systems Engineering, the Harmony MBSE Design Book, Real-Time UML Workshop for Embedded Systems, Real-Time Design Patterns, Doing Hard Time, Agility Time, and Design Patterns for Embedded Systems in C. He's formerly Chief Evangelist at IBM and currently the Senior Principal Systems Engineer at MITRE. So Bruce, with that, the virtual floor is yours.
Awesome, thank you, Dan. Let me take control here. Okay. All right, should be up. I see it on my screen. So welcome everybody to this first in this Lunch and Learn series. What I want to talk about today is an introduction to, model-based engineering. What's a model? How do I know I've done a good job? What does a good model smell like? So I've already had the introduction to me from Dan. So I will skip over this introduction slide next. Fine. All right, we can skip over that and get to some of the series. So we saw this before in a different form. The series that we're doing in this Lunch and Learn, we're starting off introduction to modeling, but there are other topics which may be of interest to you. And as part of the course today, there will be a giveaway of an autographed copy of one of my books, the latest book. The rules are you must be present to win, and at the end of the session, your name may be called. You have to acknowledge that, or someone else be selected. Them's the rules. So with that, let's go ahead and get started and talk a bit about modeling. So this is where I really want to start. People talk about, well, I did this model in Visio or I did this model in PowerPoint. Well, let's talk about the difference between a drawing and a model. A drawing is a picture with imagined or loosely managed semantics and no underlying repository information. It's just a picture of something. And the notion is you do some sort of notional work here. I need something kind of sort of like that. And then you go somewhere else, some other tool environment to do the real work, whether it's Emacs or a VI for banging out code, or your CAD or your System C for electronics, whatever it is you're doing. You go to some other environment to do the real engineering work, or Excel or Word or something. That's not what a model is. So first of all, model is always an abstraction. We'll talk about this on the next slide. Model is always an abstraction where we focus on some properties of interest and ignore other properties. So there's always an abstraction because we subset the aspects or properties of the system of concern, and then we represent them at different levels of precision necessary to achieve the objectives. And you might have many different models of the same thing if you have different sets of objectives. If I want to look at a model around, how much power can I get out of this engine, I only model the properties of the engine around that. around, it's how many pistons it has, the force per piston, energy lost along the drivetrain, things like that. I wouldn't model maybe how much it costs, or maybe the size of the engine, or its weight, or its color. Those are properties of the real system, but it's not relevant to questions we're trying to ask about how much power can I put out. So models are always focused abstractions to achieve some particular set of objectives. We capture models in a more precise language than natural language. So natural language is wonderful. You can, it's good for writing poetry. It's very expressive. If you want to write a poem with a state machine, that's perhaps not the most natural language which you want to capture in a poem. Although I did give my wife a very nice state machine, executable state machine poem for her birthday, and she liked that very much. But it's not perhaps the most natural language for doing that kind of work. So we represent properties so we can perform, quantifiable, quantitative reasoning about systems. We use a precise language to do so. And key to modeling is that as we do this, we identify those elements and characterize those properties. That information, that metadata, is captured in an underlying repository, which diagrams then visualize some aspects of that for addressing specific questions around the properties of interest. Now, with drawing, the only way you can fundamentally ascertain the goodness or the quality of a drawing is to look at it. You can inspect it. That's it. And so while that's good, I certainly recommend you look at stuff. It's the weakest form of verification. The reason why we don't trust Joe's code for the nuclear power plant, just because he says it's good, we test it, right? And we maybe do formal analysis, formal mathematical analysis on it. So there are other means, and we'll talk about some of those later in this talk. But there are other means for doing more rigorous verification than just looking at it and saying, yeah, seems okay. And if I need documentation, the kind of traditional approach to getting documentation of a system is to put a junior engineer in a corner and have them pound away, kind of disconnected from the information. So there's an air gap from the actual engineering metadata. And when he's typing the documentation, there's this air gap. So there's opportunity for mistakes and to creep in and for things to be omitted unintentionally. But with a model, you can create a report documentation from that based on some sort of template, typically, where you have some tool that scans over the metadata and pulls out information of interest and puts it in that report and organizes it according to the template. And so it's generated from the repositories. It tends to be have fewer defects than the traditional approach, and is far, far, far less work than replicating all the information kind of manually and by hand. So it is possible, just because you say, well, I'm not drawing because I'm using Rhapsody. It is possible to use a powerful tool like Rhapsody or Cameo to actually use it as a drawing tool. It is possible to circumvent the normal ways of working. I recommend you don't do that. One of my day job activities is to review models done in a variety of projects. I'm working for MITRE. I'm a principal as well as senior principal Agile systems engineer for MITRE. We're an FFRDC, so we advise the government on technology issues. That's kind of our role. And I end up looking at a lot of models for different kinds of systems in Department of Defense and other domains. And identifying, well, that's not really semantically valid, what you're doing there, and that is meaningless. So it is possible to kind of circumvent the normal semantic rules of the language, even though you're using any modeling tools. My recommendation is don't do that. That's just a bad idea. So what is a model exactly? A model is an abstraction, a set of interconnected system data around a system of interest and the properties relevant to some sort of sets of objectives that you might have for that model. So some newbies will say, well, we did a model so we can ask any question whatsoever of that system. And that's not really true. You can only answer questions that were in scope, that actually you've modeled that information, and then you can do analysis or assist in conclusions from that. So first of all, models have a scope and purpose. So the purpose is the set of objectives you meant to achieve in a model, and that really drives the scope, what's inside the model and what's considered to be outside the model. Is the cost of the engine in scope or not? Well, it depends on what the questions you're trying to ask. It's certainly a property of the engine, but it may not be of interest. And what you're concerned with is how much power can I get out of this engine? It may be in scope. It has to depend. You have a set of objectives that should be explicitly stated in your model. Purpose of this model is bang, 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 these things. And that determines what's inside the model. So that's one way in which models are abstractions. The second way in which models are abstractions are that they have different levels of precision. You can think about precision as the degree of information with which things are represented. Now, the real world has infinite precision. Well, okay, go down to quantum, we can have that discussion. But if you're above quantum level, there's infinite precision of information. You don't need to represent something. So, for example, if you're doing a C2 for cruise missile defense of the homeland, it's a project I'm currently involved in, and you want to understand that the JDOC talks to the Eastern Defense Center, which is part of NORAD, and we have long-range radars, and we also connect you to missile launchers, and we want to talk about communication. Well, you can talk about the logical information across that. You can talk about how the bits go across the wire. You can talk about individual radios. You can talk about within a radio that's got a transmitter and receiver and different parts and knobs and buttons. And inside the receiver, you can talk about the transistor level. At some point, you stop because further level of detail doesn't help you achieve your objectives, and in fact, obscures it. So we always limit to our level of precision in a model to meet the objectives of the model. Now, around precision, we think there's a term called accuracy, which is the conformance of typically a value to a level of precision. So for scalar quantitative values, precision can be thought of number of significant digits. So I can talk about controlling the rudder of an aircraft, and I want to move the rudder to 15 degrees. Well, accuracy says, well, I said 15 degrees, and I represent that to maybe 4 degrees of precision. When I say I move it to 15 degrees, how close do I say that's good enough? Is it 14 and a half? Is it 14.9? Is it 14.999? How close do we say that conforms to that value? That's what we call the accuracy. Fidelity is the precision of an input. So if I'm using a joystick to control that rudder, how closely can I specify I want 15 degrees? Because maybe I have this analog joystick and I might only be able to get within plus or minus a half degree. That's the fidelity. And all those things are relevant to what we model and how we model it. Good models are falsifiable. The flip side of that is verifiability. So falsifiability comes from epistemology. Statements are made that of truth. So models make statements of truth, either imperative, declarative statements of truth. And falsifiability means if that statement of truth is in fact incorrect, there is some way to demonstrate that it's incorrect. That's what falsifiability means. If I do a model in which there's no way to verify the truth, the veracity of the model, then I don't think it's a very useful model. In practice, it's not a very useful model. So good models identify means by which they may be verified or falsified, if you prefer that term. The point of this really is that models are this interconnected data. That's the model. Oh, and by the way, models have views. So many people, UML and Sysmol, newcomers, think, oh, it's all about the diagrams. Actually, that's not true. As one of the developers of both those standards, I can tell you that the perspective of the development team is it's all about the data. Oh, and by the way, secondarily, yeah, there are views, there are diagrams. They're really kind of almost, not quite, but almost an afterthought. As we visualize information, but the thing, representation of the information in precise ways, that's the point of the model. So as we have this model, we might have different views, different diagrammatic views, tabular views, matrices, and so on, which pull information out of that repository and render it visually for consumption by various kinds of stakeholders, whether they're technical or potentially non-technical stakeholders. So having said that, yes, there are diagrams. Diagrams always show a subset of the engineering data held within the model. And I rail against the windmill here when it comes to what I call eye bleeding charts. It's very common in DoD. You have these eye bleeding charts where you put every possible detail in the entire model in one diagram. I remember visiting an aircraft company in Seattle, which I won't name, where they had, this is in the 80s, they had a rendering, a physical paper rendering of some aspect of their aircraft design. And it was on E-size plotter paper, which is like 2 by 3 feet in size, using, I'd probably say, a 4-point font. And these were taped together going 50 yards down the hall. And they had, thousands of elements on this area, and they were so proud of it. Isn't this wonderful? I said, no, that's useless. I mean, if it looks good to managers, you can say, oh, look, I got circles and arrows and everything. I got lots of them. I've done work. But that's really not useful from an engineering perspective. So if that's not useful to put everything on there, how do you decide what goes on a diagram or not? So what I do is I say every diagram should have a mission, a purpose in life, a singular concept that is trying to represent, or a singular question you're just trying to answer, or a singular line of reasoning that you want to support. There's some purpose in life. And to my mind, if you've got 5 different questions, you've got 5 different diagrams, at least, possibly more, but you have different diagrams for every question. And that leads you to diagrams which are readable and usable for their intended purpose. And again, my day job is I review lots and lots of models. And models that have diagrams which are essentially unusable are usually either because there is no focused purpose of the diagram, it's just stuff what's in the model, or it has multiple purposes. So this and this and this and this and this. And it's better if you got, 4 questions, have 4 different diagrams. Diagrams are cheap, right? So to be clear, you do not model in Visio. You do not model in PowerPoint. You can do drawings in those tools. And hey, I like PowerPoint. We're using PowerPoint now, but it's not a modeling tool. You do not model in Visio. Not that I have an opinion. So uses of diagrams. Having said there are diagrams, so what do you use diagrams for? Well, there are 3 primary uses of diagrams. First of all, data entry. So if I'm doing my my aircraft design, I start identifying structural elements like blocks or behavioral elements for a structural element like a state machine, like states and transitions and signals and actions and so on. I enter those in diagrammatically. And the tools then take that and create information in the repository that represents that. And if I modify an element, it's modified in the repository. And if I have 15 different diagrams that render that particular property, they're all changed when I update the repository because they're dynamically linked. So data entry is one of the key things we do with diagrams. Model visualization. So sometimes you have a bunch of elements in your model and you say, I want to show how these work together, how they collaborate. So I create a new diagram because that's a new question. I have a mission for that. And I drag those elements from the containment tree or the browser. Different tools call it different things. And I say, show me these properties and these relationships among those things. So I can visualize aspects of the model to answer specific questions. Another good use for diagrams. And lastly, some tools allow you to do simulation/execution, debugging, execution control. And I can control those and visualize the dynamic behavior during execution in such tools. So diagrammatic views is a way of visualizing. I can do a design by specifying the views diagrammatically and creating those elements. And then I can debug it, execute it, and run it and visualize that execution at exactly the same level of abstraction. And that's a really powerful notion for verification of model correctness and model quality. So anybody who's read my stuff knows I am all about executable models. So there's this Douglas paradox that any language rich enough to say something useful and interesting is also rich enough to say utter nonsense that looks at first glance reasonable. So how do you tell the difference? That's the Douglas paradox, right? You have one language rich enough to express what you want, but problem is you're now also rich enough to say just nonsense. So to address that, I believe in computable models. So a computable model is one where I can, basically do the math. It's formally defined. I can, with enough precision, I can do the math. An executable model is a kind of computable model where the computation has a specific direction. First this, then this, then this, then this, and that's an execution, as opposed to general kind of thermodynamically reversible computation. F equals ma given two values, I can compute the third. So why do you do this? Because we want to verify the quality and correctness of our models. Models make declarative and imperative statements of truth. And by that, by declarative, I mean identify what you want to happen, but not really something exactly how it happens. In imperative, you say, okay, and this is how you do that. So I would argue that requirements are by and large declarative, and a state machine would be by and large imperative. Okay? So it's absolutely crucial, particularly system. Remember, I should say, my perspective on engineering and modeling comes from the fact that I spent 40 years building high reliability, safety critical systems, both the embedded software for those systems and the system and system engineering for those systems. And that colors my perspective on how to do things. Because if I get it wrong, it's not a matter of just rebooting and closing windows and reopening them. People die. And that does color my perspective. And if you're in a different environment, it might be okay to have a slightly different perspective. The user can just reboot their system. No, nobody cares. Okay, that might make sense in your context. If you're doing aircraft engines or CAT scanners or radiation treatment devices or missiles, no, not so much, right? Because those have definitely safety impact. So that is absolutely crucial from my perspective, that we can demonstrate the veracity of the statements we make in our model. And execution is a key way we do it. You can also use formal methods. We'll talk about really briefly about that in just a second. And the larger the model is, the more important that is, because it's easier for defects to creep through in bigger models. And the more significant the impact, the more critical that is. So Rhapsody Magic Draw allow you to build and execute models. I did get a comment from Sparks last night, so I added them to this thing. Said, we do that too, we do that too. And I haven't used Sparks in a while. When I last time used Sparks, it didn't execute models, didn't simulate them. But now they claim to. I haven't seen it, but they claim to, so I put them in the list here as well. So I want to talk about V&V and how it relates to models. So there are a couple things you can look at, concepts that people apply. Some people will say that verification is about meeting the requirements and validation is about meeting the need. Okay, I can accept that. Another way to think about it is that verification is about building the system right, and validation is about building the right system, which is kind of another way to say essentially the same thing. Okay, that's fine. This slide is really about, it's what I call a Bruceism. It's kind of the way I think about it. I think within verification, there are kind of two broad categories of verification. The first of these is what I call syntactic verification, or well-formedness, compliance informed. So as a general rule, every time you have a project that uses models, you should have modeling standards and modeling guidelines. If you want examples of that, you go to my website, bruce-douglas.com. And on the papers page, there are example modeling guidelines. And you can customize or tailor it. And there are others out there. You don't have to use mine, but there are others out there. But they say, so you organize your models in this way. You should use these naming conventions. These are the typical work products we expect. Diagram forms you expect to produce. You have to address these concerns, for this kind of a model, those sorts of things. It's well-formedness. It doesn't mean that you're not making sense with those statements, but the statements are there. So it's compliance informed, not necessarily compliance in meaning. For process compliance, which is important for safety critical systems, you'll have audits where you generate evidence that you have this process which has previously been demonstrated to meet the safety objectives of the standard to which you must comply. And audits come in and provide the evidence that, yeah, we did that. We did what we said we were going to do. For work products like models and model views and model elements, we do syntactic review, where we look at it and say, and you can go through the checklist and say, so did you avoid line crossing? You have a comment in the upper left-hand corner of the diagram that says, the purpose of the diagram. Did you follow the canonical model organization principles? Those sorts of things. Is it well-formed? Right. In some cases, you can automate this. In some cases, it's done by inspection. The other kind of verification is what I call semantic verification, or compliance and meaning. And this has to be done by engineering personnel and subject matter experts. And there are three basic techniques. One is semantic review, where you have subject matter experts look at it. Okay, that's fine. And I certainly recommend that. If you look at the Harmony process, of which I'm an author, there are workflows in that describe, how do I evaluate, effectively inspect a model for correctness? How do I deal? What are the steps involved, and how do I run such a meeting, such a process? So okay, fine. So, and that's good. However, it is the weakest means, and it's weak for a couple of reasons. One reason is that some kinds of problems are just difficult to see visually, but they're easier to detect by other means. Another problem is one of vigilance. Some of you have probably been on requirements reviews. And if you got 15 requirements, not so hard, right? Take you half an hour, you bang out questions and issues, and you're done. But what if you have, say, the Boeing 727, you have 200,000 requirements? What do you do in that case? And so after a while, vigilance lags, and the quality with which you find the problems degrades over time. So the next step up is testing. Testing where you have a set of inputs with a particular set of values, sequence, and timing, and have a known and expected outcome or output. And you say, I expect in this case, this test case, I'll get this outcome or this output. And you have then a set of those, a test suite that you apply. This is much, much higher level quality of verification, depth of verification than just looking at stuff. But one is expensive. It requires executability. It means you have to build executable, computable models. You don't apply this to models. So with regard to expense, 60% of the cost of embedded systems is in testing them, not in their actual original development. So it's expensive. And you can get increasing levels of coverage at increasing levels of cost. But it is impossible to fully verify because there's essentially an infinite combination of all the inputs with all the different values, all the different sequencing, and all the different timings. So you're not going to test an infinite set. You have to cut the line somewhere and say that's good enough at some level of coverage. The next step up from there is formal methods. And that's where you use typically language like Z, predicate logic, temporal logic. And you can do things like theorem proving, reachability analysis, and other kinds of formal quantitative analysis. It is the strongest means. There are things that you can verify using formal methods that you cannot verify with testing. If I want to say, I can guarantee in this system with 4 elevators and 10 floors that you can always satisfy a request in 3 minutes. Or 5, whatever the number is, 5 minutes, 10 minutes, whatever. That's not something you can test. You might do 1,000 test cases and never find the one edge case where that's not the case, where that doesn't happen. But you can do formal theorem proving. Okay, it's really hard to do though. And it's also highly subject to invariant violation. So like Gödel said, that every internally consistent system relies on external invariants. And for that reason, if you violate those invariants, you can't judge your conclusions. So if Susan is on floor 6 of elevator 4 holding the door open, and the elevator motor for elevator in shaft 2 is broken, that invalidates perhaps your assumption of your proof. But collectively, these are the techniques used to verify the correctness of your model. And lastly, we've got validity or the relevance, I guess, is another way to think about it, of your solution. Are you solving the right problem? And this becomes a problem because there's always an air gap between requirements and the system need that is trying to the need the system is trying to address. The theory goes that if you build a system with these properties as required by the requirements, it will meet my need. But that's really an air gap. Department of Defense did a study where they found 45% of the systems that they require cannot be used for original purpose because largely, not entirely, but largely because the the requirements didn't really specify the need. Right? So having said that, there are ways that we can perform validation. Commonly, we review. So if all you can do is look at something, you got drawings, then all you can do is review it. And again, that does add some value, but there's still issues with that. You can also do simulation, even early on, around some capability. So you're doing maybe a use case or a capability analysis for a system, and you build this executable requirements model, something I do all the time. And then you can do what if. Well, what if the pilot does this, and the enemy does that, and the missile does this, and the ground system does that? And what about that case? Well, you can actually run that simulation of your requirements model and say, well, this is what we specified will happen. The traditional way is just kind of thumb through this page of thousands of requirements and try to find that. And that's problematic, let's say. You can also execute in a sandbox. We have this constrained environment. You can do early flight tests in some sort of operational environment, demonstration of system capabilities. And you can also do deployment, even deployment sometimes of not completely capable systems, but you get a feel for how well they address the needs of the stakeholders. So there are approaches for doing validation as well. So when I think about verification, validation of the quality, falsifiability of my models, this is what I think about. So INCOSE, this is kind of a slide summarizing this document from INCOSE, has a organizational model-based capabilities matrix from level 0, where we have no model-based system engineering capability, to level 1, we've got some limited use for and to answer specific questions or address specific needs, to a kind of standard way of using modeling for different things, to widespread use of modeling throughout your projects, to deployment as a standard approach with a reusable set of digital engineering assets and platforms as the standard way of addressing your engineering programs. So there's different levels of maturity kind of at the organizational level. And that actually aligns pretty well with this maturity model that I've had for a number of years for kind of project level modeling maturity, where you start off with siloed document-based, text-based approaches, where you have heroic efforts to deal with all the issues that come up with disconnected siloed data that isn't precisely represented, to visualizations of engineering data, to standardized approaches for using modeling that employ things like the notion of single source of truth, and the use of modeling guidelines and standards and strong integration engineering process. The next step up is to build, falsifiable executable models in that context, and use of quantitative metrics over model quality, and also as well as kind of program metrics as well. Up to level 4 is where models are used as the core basis for all engineering work. This forms the core environment in which you do your engineering work, and that's the most mature level. And since one of the things I do is I was brought into MITRE from IBM with a mandate to elevate the engineering capability of MITRE as an engineering organization with respect to digital engineering and models. So that's kind of, I spent a lot of my time kind of focused on that. We're elevating the level of maturity of organizations and projects so they can get more value out of their modeling efforts. So in Sysmol, the number of different modeling views, we have functionality, and we'll talk about these pillars. So we have use case diagrams, requirements diagram, requirements tables, requirements matrices, and so on. We have things around structure, like in UML it'll be class diagrams, and Sysmol it'll be block diagrams to represent the type structures. For how they connect in real world, what I call the connected design or connected architectures, we use internal block diagrams or composite structure diagrams. For interactions, we use sequence diagrams, or my favorite view, timing diagrams. For flow-based behavior, using token flow execution semantics, we have activity diagrams. For state-based behavior, we've got, of course, state diagrams based on Hurrell state charts. And for parametrics and quantitative computable models, we can use parametrics to represent the constraints with the limitation on values and how they connect to build up computational models where we can evaluate quantitative properties of systems. So Sysmol and UML, as I mentioned, I'm a contributor to both these standards. And Sysmol is based on UML. They're the subset that, not everything in UML is in Sysmol. There's a subset. And that subset brought over is called UML for Sysmol, formally in the standard. So there are these 4 pillars. So this is was identified by Chris Coburn, who was the lead of the UML for Systems Engineering RFP effort originally, and the Sysmol partners effort. So he kind of quoted this, and I've changed it a little bit because I don't exactly like how he did that, but it's very close to what I have here. The first pillar we'll talk about is structural. One of the things, so in the early 2000s, late 1990s, I was doing system engineering with UML with a variety of customers, aerospace and defense customers primarily. But there was this kind of thing that, well, we can't use UML because UML has classes and we have blocks. So we changed the name of class to block, and all of a sudden they said, oh, we can use it now. And it's a little bit more complex than that, but that's really basically true. So there are some things which are used as is, packages, operations, profiles, stereotypes, interfaces, and so on. And there are things that are renamed. They're just renamed. And there are things which are kind of new fundamental types. In Sysmol, we renamed class to block, object to instance part, instance specification. Attribute became value property. We also added the notion of dimensions, which was later changed in Sysmol 1.3 to quantity kind, and units. So meters, furlongs, pounds, ounces, lumens, units of measure. And there's an optional compliance point in the standard to include the ISO 80,000 library of international standard units. A class diagram became block definition diagram, composite structure diagram became internal block diagram. So what Chris referred to as requirements pillar, I prefer to think of it as functionality. This is kind of declarative functionality. Requirements, use cases are used as is, use case diagrams as is, but we also added the notion to UML of requirement. Yes, I arguably think that requirement should have been part of UML, but fine. When we started to work on Sysmol, it wasn't, so we added it into Sysmol. And we added some views around that. For behavioral imperative view, not all the diagrams made it, so communication diagrams made it, timing diagrams, unfortunately. And I kind of created those for UML2 and shepherded them through the approval process. And I was kind of sad face, that they didn't make it into Sysmol. Because for me, in my world, timing and explicit representation of timing are really important for correctness. And it's not a really good way to view that in Sysmol. You can kind of sort of get there, but it's limited. Interaction overview diagram, nobody used, so that's fine. State diagram, activity diagram, sequence diagram are used pretty much as is. Activity diagram is extended. The big extension in activity diagrams is we added the notion of continuous behavior. Normal activity diagrams execute via token execution semantic. So when an action is done, it sends a token to the next action or next set of actions in sequence, which means it's very much discrete because it's handed off at some point in time. So how would you model? So if I'm going to send to a water heater, set this as the temperature, there's a discrete message, set the temperature to 90 degrees. I can do this very discrete. What about the water flow from the water heater into a tub? How do I model water flow there? That's a continuous flow. And so we added some additional notions like continuous behavior. We added probability of firing, so we can do Markov chain analysis. And so there are some I think, relatively minor extensions. And the last pillar is in parametrics, where we took the notion of a constraint, this limitation of values, of quantitative values. And we added constraint blocks and parametric diagrams, constraint properties to kind of build up these computational arrays, connected arrays of constraints to do the math, essentially. A point I do want to make that really UML and Sysmol are the same language. Sysmol is subsetted, and there are some extensions, but under the covers, it's UML in system engineering clothing. It's not so true in Sysmol 2, which is a little bit ways out. There's the notion of architectural frameworks. These are frameworks is an encapsulation of practices, requirements, and representations for work products that capture system architecture. So you may be familiar with DODAF, it's been around for quite a while, or TOGAF. And then UPDM and UAF are representations of DODAF, and UAF is kind of like version 3 of UPDM, using UML Systema actually as the underpinning. And there are other standards like DND, DNDF for Canada, NAF for NATO Architecture Framework as well. So these you can also think about these, which are at least conceptually derived from the Zachman framework, where you have some sort of area of information versus a domain of interest matrix, and you have different views in the different areas of inside this matrix. And it's really explicit if you look at the UAF spec. Let's talk a little bit about UML. Current version is 2.51. It was standardized, started the first release is 1995, was standardized in 1997. That was version 1.1. And it's really a modeling language for MDD, for model-driven development of software. Supports, but doesn't require object-oriented approach. It is process agnostic. So intentionally, on purpose, we excluded the notion of process from UML. It's basically a language. And separately, you can define what process you might want to apply. And using tools and languages like SPEM, the Systems and Software Process Engineering Meta Model, which is a separate standard from UML. It's a graphical language in which you express things diagrammatically, which then again gets entered into this underlying repository. Packages or model elements used to organize your models. It's just a package is a model element that contains other model elements, including other packages. And one of the kinds of things it can contain is diagrams. So I have different types. And within a type, like a block definition diagram, you're going to have different intents or purposes or missions. I call that diagram usage. So the semantic basis is this 4-tier meta-model hierarchy. So at M0 level, that's the aircraft flying in the airspace. At the M1 level, that's the blueprints of the design of that aircraft. That's called the user model level. At the M2 level, that's the definition of the language in which you capture those blueprints. That's UML or SysML. That's the meta model. And at M3, then you have the meta model, which is the language in which UML itself is defined. And if you ask us for more depth, then we change the subject. So it's shown over on the right-hand side. You got these 4 levels, and it's like meta turtles. If you're familiar with maybe Pratchett's writings, it's kind of meta turtles all the way down. It's a way of organizing the models, which makes it a rigorous structure, but a kind of a complex structure to read and to grok by reading the standard. There's a number of diagrammatic forms. Most important here would be probably class diagram, activity diagram, use case diagram, state machine, and sequence diagram. And the other ones certainly have value, but those are the kind of certainly the primary views. Then there's SysML, which is our primary concern as system engineers. So in a joint effort between the OMG, the Object Management Group, it's not, oh my God, it's Object Management Group, INCOSE and AP233, we developed this response to that RFP called SysML, Systems Modeling Language. And it supports specification, design, analysis, verification, and validation of systems which are not entirely software, right? They may contain software, they don't have to. They may contain software. But mostly we're focused on doing system engineering, which is a specification of systems properties, more or less without regard to whether they're software or electronics or mechanical or chemical or whatever aspects of it. The use of models for system engineering is called MBSE, model-based system engineering. But remember a couple things. One is UML, SysML are really the same language under the covers, minor naming differences, at least at the basic level. And that, like UML, SysML is process agnostic. Here's a kind of a history chart. of UML. It's the first release of UML, again, finally standardized in 1997. Peter and I released the Harmony engineering process, Harmony SE process. What was it, about 97, I guess. And we work with a number of companies to use that process, to use UML for modeling. But again, people said, you know, we have issues, we got classes here, we don't want classes, we want blocks, dang it. We wrapped up work on UML 2.0 in 2001, and we began work on the Sysmol standard in 2001. 2003, we had the initial release of Sysmol for adoption, but in the OMG process, there's a finalization effort. That took 3 years. So 2006, we finally had the adopted standard of the Sysmol. Now, Sandy Friedenthal, who was the lead, technical lead for the development of Sysmol, with Alan Moore and Rick Steiner, published this book, Practical Guide to Sysmol. Similar, about around the same time, I took the Harmony process and adapted it to use of Sysmol now, and the use of Agile technologies, Agile approaches into the process. And that's available on my website if that's of interest. And in 2017, I published my Agile System Engineering book. Around that time, work was started on Sysmol 2.0, which is a pretty major overhaul of the language. 2019, Sysmol 1.6, which is the current standard, was released. And then earlier this year, I released the latest book of recipes or workflows called the Agile Model-Based, Mandela-Based System Engineering Cookbook. If you want to know more about the standard, if you're a bit of a masochist and you want to read the actual standard, there's a link here. You can go track that down. It's kind of dense reading, frankly. There are 9 diagrammatic views and a couple of kind of tabular forms. Some of these are used directly as is from UML. Some of these are modified. So really, it's not so much the diagrammatic form itself is modified, but the elements that they show have modified. They're renamed or modified in some ways. And those are the ones in blue. And the ones in red are new forms. Requirements diagram, parametric diagram, which is a kind of internal block diagram, which again, a kind of structural composite diagram. Allocation matrix and requirements table are our new views in Sysmol. So this is kind of my take, some of it's my take, on Sysmol views. So we have the views with their abbreviations over on the left, and then the kind of view is static functionality, dynamic behavior, and so on. If there's a direct UML2 analog for it, where it might be used. So I think the other column is the more interesting part. I think there are 6 kind of really essential views in what system engineers are doing today. Use cases, so you have to reason about capabilities. I think that's really important. And then you have these behavioral views, 3 behavioral views, activity sequence and state diagrams. To represent structure, you need to have 2 views. One shows the types, box R types, and their properties, and how you build collaborations from them. And that's on BDDs. And you need to be able to show the connected architecture, how they actually connect in a running system. And that's shown on IVs or internal block diagrams. 3 of these views are really essential for dynamic simulation, the behavioral views. And for just generic computational views, we have parametric diagrams. Code generation is not a critical feature for system engineering, because the outcome of system engineering, I would argue, is specification, not implementation, at least kind of left side of the V, kind of the side of system engineering. But some of these views are involved in code generation if you want to do that. And lastly, on the right-hand corner there, the edge, we've got the more formal views. Some of these views, like requirements diagrams, use case diagrams, they rely on some natural language and expressions. They don't have deep formal semantics. Other things do have more deep formal semantics, as these identify the ones which have those formal semantics. So as part of the work I'm doing with MITRE and others, I created this curriculum. Each one of these boxes represents a course, and each course, these are all 3-day courses. So the idea that you can learn SysML in a 3-day class, training class, is, I think, just wrong. That is just not my experience. So I've developed an entire curriculum for how to do skill acquisition. And so a master's series in this curriculum is a path all the way through to some endpoint. And we have a requirements, a curriculum, master's curriculum, and an architecture master's curriculum right now. And there's plans to add more stuff here. The Common Core, SysML 101, basic, all the basic views, but really not in great depth. And then the 201 gets into more depth of structural stuff, data schemas, a lot more about ports and flows, and a lot about parametrics and building computable, and in fact, executing parametric diagrams. And the last is 202, which is about advanced behavioral modeling. It's just activity diagrams and state machines. And it's a pretty full 3-day course. And then we have Introduction Requirements 101. That forms what we call the Common Core set. So I want to do just a quick walkthrough of an example. What does it kind of look like? So in my book, the one that we're giving away today, I did this Pegasus Smart Bike Trainer. I'm a Ironman athlete. I do Ironman triathlons. I do ultra marathon cycling, 24-hour cycles and 500 mile, that sort of thing. Race across the West, 900 miles, 150 miles, that sort of thing. So that's where I spend my spare time. So for the example in this book, I created the Pegasus Smart Trainer bike. And this shows the package structure. This is shows the package structure organization of that model. This shows the sets of requirements and requirements table, where we see the different columns. There's a name column and a text column with a textual specification. You can also show an ID column and other columns as well. Here's the use case, a use case diagram showing 3 or 4 of the capabilities. We modeled as use cases. And emulate the basic gearing, front and rear gearing, measure performance metrics, and call resistance. Each one of these then traces to a set of requirements, and you build up this computational executable model around that and so on. But this is the kind of the basic view, and it connects, for example, to a training app. There's some standard web-based training systems like Sufferfest, Training Road, Zwift, and others out there that you can connect to. And of course, it interacts with the rider on the bike. And you also have an application to configuration that I can select what your gearing you want to have available and so on. This shows the type context, the context of the system. Here's the system as an element with connection points called ports. We've got our interface blocks defined up here. We've got our actors. In this case, this is the Cameo model. The book actually has the models as Rhapsody models. And just for this purpose, I created Cameo versions of these. I create a block that represents that actor, because in Cameo, I can't add an actor to give me a port to an actor. So I basically use a stand-in called an actor block to stand in for that. So I can build up and execute my context, my system context as a feature. I can execute and simulate it and do behavioral analysis. This is a pretty common sort of view that you'll have in UML SysML. We've got the system, and we've got the various kind of subassemblies or subsystems, the mechanical frame, powertrain, comms. This would be Bluetooth and FEC, other kind of connection modalities. The rider interaction subsystem, where we control gearing. I can change my gearing with an interface. I can visualize the gearing. I can also incline, decline the bike. I have electrical power delivery, and I've got a mean kind of computing platform, which this system actually, as you push on it, it'll create resistance using some internal mechanism, such as an electric motor. So you can do like rides on simulated terrain where you go up hills, down hills, and race and do sprints and all these things on that, and it provides resistance based on the terrain and what your profile looks like. So this forms what we call the type composition architecture on a block definition diagram. This shows how does the system all connect up. This is an internal block diagram showing parts. Those are the roles. A part is really a role an instance of a type plays in a particular context. And they show the parts of the system connected up with connectors to the external ports of the system. So this shows that internal structure. This is a parametric diagram doing a trade study, looking at different alternatives for selecting how we generate resistance. Whether you want to use a hydraulic system with a variable aperture valve, whether you want to do some combination electrical hydraulic, or you do electric motor, you want to use wind turbine, however you want to generate resistance. What are the alternatives and pros and cons? This allows us to build a computational model to perform that trade study. Here's just an example interaction for a use case model. We've got the use case, we've got our actors, and we can talk about how they interact over time and represent the signal exchange between the writer as he moves the pedals around, and we compute resistance and do computation of inertia and so on to do the math to determine how much resistance should be applied at the point of the pedal. There's the flow of control behavior. This is for the computation of the bicycle physics and execution. So this is again, executes via token execution semantics. And these are different actions that are performed as we basically do the math, and we go back and do some more math over time. This is a loop that goes on as we're running the system to continuously update the resistance depending upon what the writer's doing, as well as what the train looks like. A very simple state machine for part of the system that talks about how to emulate gearing. This is again for use case. How do I emulate gearing? So everything on here represents a requirement in some sense because it's a specification state machine rather than a design state machine. So if you want to know more information, this is, again, I realize it's kind of a fire hose, brief conversation. If you don't know more, you can feel free to come on down to my website. It's all free. We have papers and presentations and forums and stuff. As I mentioned, I've written the occasional book. With that, I'll throw control back over to Jack or to Dan.
Thanks, Bruce. So I think our winner for the book today is Carolyn Booth. Carolyn, we have your email information. We will send you an email and get your mailing address, and let us know which of Bruce's books you'd like. We'll get you an autographed copy of his book. Thank you very much for attending. We're a little bit over on time, but since this is being recorded, how about we go ahead and get to some questions? And let me get to the first one here. So can you elaborate on the architecture framework, how they relate to Sysmol? Is it just another way to show diagrams using Sysmol language when it relates to MBSE? Okay,
so the architecture frameworks provide practices, which are process fragments, right, workflows, as well as a semantic basis representing systems. So if the ones I've talked about, UPDM, UAF, and so on, those are based on SysML underlying semantics. So it's what we call domain-specific language, DSL. So we take the underlying language as the basis and then say, we have a special kind of that. So we have, for example, UAF, we have the notion of resource. Well, it's really a kind of block, right? So it's really a kind of block. But in the domain of discourse, in this case, the architecture framework, we want to talk about resource versus systems versus capability. Those are different concepts. And we want to relate those concepts from the domain and represent them using SysML as an underlying language architecture. So the really domain-specific language based on SysML as a reputational format, along with adding some practices and use the framework for those kinds of systems.
Yep.
Question. So if you were using UPDM, would it be okay to express your elements as blocks, or should you use the resource to represent your elements?
I think that's a great question. And the answer is, it's up to you. In my experience, most people who want to use DODAF work products, and I do a lot of that, use Sysmol directly. They don't use it UPDM. It is more common, in my experience, to use Sysmol as a language. However, there's an option. If instead you'd rather use UPDM, it is a more specialized, also more complex language for expressing those DODAF products where uses the DODAF vocabulary. Under the covers, it's still Sysmol, which is DODAF vocabulary. So in my experience, most people use Sysmol for that purpose. But it's okay to use UPDM. It's specialized it's expressly for that purpose.
Okay, thank you.
Okay, thanks. John has a question. What if any future improvements to Sysmol are being discussed?
Oh my God, that's a big topic. This is a great one to hand off to Sandy. And the answer is kind of yes. They want to maintain some backward compatibility with the Sysmol language itself, because what it actually does pretty well. There are places where they want to clarify things to make them align better. But in addition to the language itself, they also want to tie in tools and tool APIs into that as well. That's something that's not at all addressed by the current standard. So that's a new area that expresses. So not only are there, one could argue defect repair or additional specializations for system engineering work products themselves, but they're also addressing some new areas of subject, such as I mentioned, tools, tool compliance, and tool APIs. That's a big topic.
Okay, thanks, Bruce. Andrew has a question. To what extent does this curriculum prepare students for OCSMP certification? And this was whenever you were going through your curriculum slide on Sysmol 101, 102.
Yeah. I would say it doesn't really address that concern. I wasn't really, I didn't base the curriculum based on this is the test you have to pass. Rather, I based the curriculum on you're engineers, this is what you have to be able to do. This is the capability you as an engineer must bring to the table. And so because of that, I didn't focus it on passing the test. So it's really meant for, it's not really meant for certification. If you wanted to get certificated, if that's your purpose, there are people who have classes out there to prepare you for certification, but that's a different task than enabling you to be a better engineer or use these in engineering way better.
Okay, thanks, Bruce. Terry has a question. What are the pros and cons between Sysmol and UML, function flow block diagrams and its derivatives, and object processing language?
I don't know object processing language. I can't speak to that. UML is the language I use preferentially when I'm doing MDD, model-driven development. And again, my world is embedded systems, but you can use it for general software development. And Sysmol is what I use preferentially for systems engineering work. So I'd say that's kind of the difference is kind of the target. Sometimes I'll mix a mixed project where you do the systems part in Sysmol and you hand it downstream to people using UML. At that point, they basically throw off the covers and they expose the fact that it's really UML in the covers. So I hope that answers your question.
Okay. Got another one from Bill. Can you discuss what is a Sysmol stereotype and when to use them when you want to create a new stereotype?
Stereotypes are a way, so remember M0 and M1, right? M0 instance model, M1 is our blueprint model, user model, and then M2, your UML language. So stereotypes basically exist at level M15. they're a lightweight way to extend your modeling language. So you might, for example, a use would be, I've got an operation, but I want to add metadata around the operation because I want to, in a real-time environment, understand what's the average execution time, worst case execution time, what's the deadline, and the jitter around that execution. I want to capture that real-time information around performance so I can do a performance analysis. So one way to do that is say, well, this is a special kind of operation called a real-time operation. And I add those in my stereotype as basically attributes of my stereotype. They become tags or tag values for the element. So it's a way of extending information represented by an element, a way of extending your modeling language. And so you would use it whenever you want to extend your modeling language. I think it's an overused thing. Usually, most of the time when people do meta modeling, they should really be doing modeling. That is, you rather than say, I've got a stereotype for electric engine, and it is a special kind of stereotype over engine. That really should be an M1 thing. You've got an engine subclass to another electric engine. This usually should generally be doing modeling rather than meta modeling. But stereotypes are a defined way that you can extend your modeling language. Sysmol is in fact extended UML by taking UML elements and stereotyping them to create a new modeling language for system engineering.
Okay, thanks.
Yeah, that's the short answer.
How does a Sysmol model translate into or integrate with an assembly model in a PDM system? Anoop wants to know.
Well, remember that the example I gave of the Pegasus model, where we had let's go back to here. You can think of this as like a parts list in some sense. So from a type composition model, you could in principle say, well, these are going to be my primary LRUs or pieces, components I have to create and manage my PLM system. You could have that kind of connection to PLM system if you wanted to. So that's kind of how I think it's. A PLM is typically identifying the structural elements you're going to construct, and then you have the my list of my pieces, my inventory, and how do I assemble them? And how do I assemble them is then shown by this connected architecture. This is how they get assembled and how they get connected up. So I think there's a pretty strong relationship between those in principle.
Okay, thanks. Esteban has a question. Hello, Bruce. Thank you for the talk. In summary, if possible, in a couple sentences, what does a good model smell like?
It smells like victory. Easy one.
Okay. Okay. Good deal.
Okay. Let me say, okay, let me elaborate that a little bit. It smells like it is, you've got well-defined purpose and scope, a defined level of precision necessary to achieve your objectives, and it executes and is verifiable.
Okay. Jamie just popped up a question. Could you please share your perspective about the state of the art in MBSE integration and data interoperability, most promising technologies?
Okay, so for interoperability, there's a standard called FMI. So we talk about federation of models. There's a standard called FMI, the Functional Markup Interface, which is specifically targeted towards building hybrid simulation models. So for example, the Crystal program done a few years ago now, where you have a structural model was done in I forget it's UML or Systema, I think it was UML, defining structure and state machine behavior. You have a control loop done in Simulink. You've got Simulation X, or this one was Mandela doing like environmental and weather models and so on for aircraft de-icing system. So is there a standard way in which we can federate such models for the purpose of simulation and analysis? And so yes, there are ways to do that. A different answer to the question would be around sharing models between tool environments. That's problematic, I have to say. So there is a standard called XMI, which is the XML model interchange standard. And it's frankly lossy. Interesting story about that. All of the tools of which I'm aware share an implementation created by Sodius, a French company that creates the XML interchange tools. And yet, if you go between Cameo and Rhapsody or the other tools, there is information loss. It's not a lot necessarily. Typically, it's around diagram forms, but there's some information loss that you have to, stuff that you have to redo. So anywhere from 90% gets exchanged. They have released a new tool recently called Publisher, which specifically addresses moving from Rhapsody to Cameo. And it does a better job than the standard import. Still not 100%. So yeah, I'd say it's a bit problematic, the exchange of models between different tools. And yeah, it's a shame.
Okay. I think that's the end of the questions that I saw. Jack, any questions from that were submitted before we started? Yep, I saw Jack come off, but I don't hear him. Maybe we lost him. We're way over on time anyways. So thanks a lot, everybody, for attending. Bruce, thank you for your time and giving a great talk. And stay tuned. October 6th, we'll give the next one on Agile MBSE. So thanks for attending, everybody. Have a good day.